Good evening, everyone. This is Tony Miracker. I'm the section chair for the Toronto section. Welcome to our November meeting. It's great to see a lot of people that have are starting to come into the queue to participate in our meeting. Just a few things that, if I may, Toronto's Technical Conference is sponsoring tonight's event. We hope it will be a face-to-face, but the jury's still out on that. But in any case, we will be doing this event virtually in conjunction with, if we can, but if not, we will do it virtually. So mark in your calendar, in June, we will be doing a Toronto Technical Conference two-day event. Couple of things here just to let you know that tonight's meeting is recorded or is being recorded. Part of the registration that you did, you'll be receiving an email either tomorrow or the day after tomorrow with a URL to our Facebook page, or our YouTube channel page that will have the recording once we slice and dice it and convert it from GoToWebinar Speak to YouTube Speak. Future meetings, our December 8th meeting, we are working on James Snyder and his group to talk about the NASA Apollo Audio and Imagery Restoration Project. That hasn't been confirmed yet, so we're working on that. We have a backup plan, and we'll let you know in the coming days on what we will be talking about, but right now it is scheduled for December the 8th. That meeting, we will also have some prizes and some giveaways. So do mark it in your calendar, because we will be giving, I know one thing that we're giving away is a 1-year professional membership. So do mark that in your calendar. The January meeting is going to be COVID onset related. We've done COVID related first into the back end of the studios and post-production, and what people have been doing in control rooms working remotely. But this one's going to be geared for onset COVID reality. They have their own challenges and different challenges, because there are people that are, many people that are involved in onset productions. February will be a student focus, where we will pick a bunch of topics that speak to the students. So we did that last year as well, and it had we had a great response. On this evening's presentations, we will, I'll have control here, and I'll move the controls over to each of the presenters, and they will then speak to you. Assisting tonight will be the co-organizers, who will be reading bios and introducing each. Questions will be at the end of all presentations. So, and Paul Briscoe will be manning the chat room and the question area. So type in your question into the chat room, and Paul will then ask the presenters your question. Oh, I skipped over. Now, Paul, if you want to spark yourself up and take it from here, and I will start moving presentation over to Peter.
Once again, good evening, everyone. Good morning, good afternoon, depending where you are on the planet. My name is Paul Briscoe, and it's my pleasure to welcome you to this evening's presentation. I'd like to thank and introduce my co-organizers, Lee Whitcomb and Gleb Butuzov, and those two guys have done the bulk of the work, along with Tony Miracker, to put this all together. So I thank them, and we hope you enjoy this evening's presentation. It's a real pleasure to welcome you. Thank you for taking the time to join us. We hope it's valuable to you, and we hope we give you some useful knowledge tonight. We know your time is valuable, especially your personal time, And so if that's the case, a special thanks for you joining us. Tonight's presentation is called Forecast Cloudy for the Foreseeable Future. We were trying to think of a clever title to talk about the cloud, and it occurred to us that this is something that's not going away anytime soon. Not to say it won't be sunny days, but it's going to be with clouds. You know, it's invaded our lives to an extreme degree. If you carry a phone, if you use a computer, if you watch any kind of TV that isn't over the air through an antenna, somewhere the cloud is touching you and you're touching the cloud, whether you're banking, whether you're shopping, it doesn't really matter what you're doing. And it's throughout our lives already. And it's now reached a point where it offers us the capabilities of doing what we do for a living, which is media. So that's what we're going to talk about tonight. We're going to talk about what the cloud is and what we can do with media in the cloud today in the context of live production. And we have several very specific targeted presentations to address this topic. Quickly, what is the cloud? For those who aren't familiar, it's a giant connectivity network full of compute horsepower. And that's the simplest way to put it. And you're going to learn a bit about how that gets used tonight. And we're really only the tip of this iceberg. So this is probably the first you'll see of many, many presentations on the cloud and the future of that. For example, Starlink, Elon Musk's Starlink satellite cluster is now in operation. They've got 600 or 700 birds up there now, and you can buy for $500 US, you can buy an Earth station. For $100 a month, you can get 100 megabits down, 50 up. And that's pretty cool. That's a serious game changer. So what we call the cloud today, with that kind of connectivity, becomes yet again another thing. And now imagine if, for perchance, we put compute power into orbit, where cooling is prevalent and energy is free. That's a whole new thing. So, you know, this expanding world will continue to amaze us. But tonight, with feet on the ground and head in the clouds, let's talk about a few things. So first up, to give us some context, is my good friend Peter Wharton. Peter is the Director of Corporate Strategy for Tag Video Systems, which makes innovative all IP monitoring systems. He also serves as an advisor to other industry-leading media technology companies. He is the founder of Happy Robots LLC, a media technology engineering, development, and consulting company that focuses on creating transformative cloud-based media operations through intelligent, cost-managed, and highly automated end-to-end workflows. Peter has also held a range of engineering, product management, live production, and business development roles at Grass Valley, Broadstream, PanAmSat, Fox, and ABC networks. A SMPTE Fellow, he currently serves as SMPTE's Membership VP. He is the incoming Education VP and previously served as Secretary Treasurer and Eastern Regional Governor. He's produced Bits by the Bay for many years, since 1999. Over to you, Peter. Peter Wharton.
Right. Thank you, Paul. First, can you see my slide? Are you all seeing my slide deck? And you're muted again, Paul. So
yes, we do, Peter.
Thank you. Okay, good. All right. Well, thank you all, and thank you, Toronto, for hosting me and hosting this. This is great. So let's dive right on live production in the cloud. So when we look at live production, there are four main accelerators that are driving this at this moment. The first is that there already are organizations running in the cloud, such as esports companies and companies that are OTT native. So they've never had the need to have on-premise production and such. They've started that way, especially because esports, starts electronically to begin with as games. It's a logical extension of remote production, or REMI, what we've been doing already, where we've been doing at-home production. We bring all the signals from a venue back to a centralized production facility, which is driven really by economics. And of course, COVID-19 is driving this with people having to work at home in a more distributed fashion than even REMI. And finally, there is an ongoing pressure in the industry to move away from CapEx into OpEx because the workflows keep changing, because the business disruptions come faster than ever before, and therefore putting scarce capital resources into physical facilities that may be out of date before you finish building them becomes riskier and riskier. So moving to OpEx and moving to where you can rent infrastructure in the cloud may make more sense than building physical facilities. But moving live production into the cloud is still very challenging. The other advantage of that, of course, is that these are itinerant workflows, so there are economic advantages in running in a cloud where you're only renting it for the period of time you need it versus owning it 24/7, even though nobody's doing live production at 3 in the morning that I know of, at least. So when you talk about moving live production to the cloud, it's probably the most complex part of a media workflow. It's lots of people working together, video switchers, with tallies, multi-viewer audio mixer with mix minuses and IFBs and recording, clip playback, instant replay in slow motion, graphics, automation, camera shading, robotics, live captioning, teleprompter, intercom, and of course the ability to split all these components amongst your operators based upon how you want that workflow to go and how many operators you want. It used to be a control room had 20 to 25 people in it. That was just the way it was done when I grew up. Today, you see people, a single person running all this through one interface in some cases, but some programs are far more demanding and still need 20 to 25 people in a control room. Or if you get into live sports and especially things like Super Bowls, there's 12 semis full of people running different workstations. So it's you need a tool, a way of actually making it adapt to how many people you need to do the work. So we look at the challenges of moving live production into the cloud. And the first one that comes up, of course, is latency, because live production is very sensitive to latency in our signals. And we'll talk about that in a minute. You also want the full applications and feature sets and control surfaces with the familiarity and ease of use that operators are used to. And of course, you want high signal quality. People really want pristine signal quality when they're doing live production. It's the first time you actually access those signals, and you want to also make sure that you've captured those and archived them in the original quality where possible. And that means you also want generally very high bandwidth to support all of that. And of course, viewers expect high quality, and there's also viewers expect low latency, although their expectation of latency is different than we want for live production itself. But they expect that when they watch a Super Bowl on TV, that they're not going to see the game, 3 minutes after somebody else who has it. So latency is still critical on the distribution side. And of course, there are business metrics, their operational costs, and the overall performance of what we do that come into play here. So we look at live production in the cloud. The traditional way we would do live production in a control room and either on site or remotely is using uncompressed SDI or 2110. We would have hardware-based processing, which is obviously not adaptable to the cloud. And we would have discrete components for each of these functions that we would connect through this network. And we've seen that there are cloud-based production solutions, which are pure software-based solutions. They're really actually not meant for the cloud. They're more just pure software, but people have been running them in the cloud. And they're not really designed to replace professional systems, things like OBS, Wirecast, and vMix. And I'm using OBS right here as an example, but I would never hope to do a live event with this multi-camera. And so we look at these and they're built for a specific purpose, more like what we're doing now, webcasting, but not really meant for live production, certainly not live sports, to most people's viewpoint. So what we really want are some new cloud native professional solutions to do live production in the cloud that are meant for the cloud from the beginning and designed for our needs. And the development of these have been accelerated by COVID. So in the last several months, we've seen products like GVAMP and TVU Producer, and VizRT, I believe, has a solution coming out early next year, and EVS and Sony and others are probably have solutions or are working on them. So we're starting to see these products appear on the market. And really, most of these take some form of integrated production where all these things come together. And I really don't know. You'd have to take a look at these to see how much you could distribute that workflow amongst multiple operators to meet your actual production needs. So making live production in the cloud actually work. Fundamentally, we want the same technologies and workflows and there's familiar feature sets. But we want to redesign systems with 100% software for the cloud. And we need to fight these inherent cloud issues such as latency and constrained bandwidth. And so these early stage migrations really were doing less attention to managing costs and more about, or even about creating opportunity, more really focused on just how to make it work. But once you get past that first phase, what's the next phase of cloud production going to look like? Well, the ideal control solution would have a new set of control surfaces. They're not geared to the old school way of doing, because we've been building production switches that look fundamentally the same for the last 40 years. I mean, we add new features and stuff, but the layouts and such and things are not really all that different. And the question is, those were built based upon the hardware requirements back then and technology limitations. What would, if we started from a clean slate, what would it look like today? And of course, it has to be cloud ready, and it has to support things like transport protocols that we need in the cloud today, RIST, SRT, and such. It has to be a modular architecture because we want to be able to break this apart, and especially with an open architecture to support third-party components. If you look at anybody building production systems today, almost universally, they're buying one company's graphic system, someone else's switcher, someone else's audio console, and each of these are sort of best of breed things. And so there's still going to be that desire to be able to find the different systems from different vendors and bring them together, especially because you might want to tie an existing intercom system or an existing graphic system to your cloud production. So you're going to have those kind of constraints. Now, when you get to the cloud, we also want to make sure this is economical. So you can't use the same system for the Super Bowl for a college game or a high school game. So it has to scale. You have to be able to choose how big a system you want to build, how many ME buses, how rich the graphics are, and be able to right size the instances you run in the cloud to create an economic footprint that you can afford for what you're actually producing. And ideally, this would be dynamically scalable during an event. You'd actually be able to grow a system or shrink a system depending on what you're doing. So, maybe in the pregame show, it's a smaller system than it is during the full game or during halftime, or there's a system that comes up during halftime and goes away in big events or something. But you need some way of scaling an event. And then what you really want is something where I can build all this, because that's not going to be easy. It's going to have complexities. I'm going to test it. I'm going to rehearse. I'm not going to put it to sleep until the event. And then I'm going to be able to launch it with a push of a button. Everybody comes to workstations, do the event, and then tear it down and park it with no cost while it's parked until I restore it for the next event, next time we have an event with a single button key. So what that really tells me is that orchestration is really the key. That's the holy grail of this, is we need a way to orchestrate all of these things in a way that makes it friendly for operators and doesn't require an engineer to come in there and write code and log into all these systems and authorize every time you want to do something. So, this is where we're heading. So there are obstacles certainly to using uncompressed in the cloud, and my colleagues coming up will tell you about a lot of these. But obviously, we're dealing with very high bandwidth signals, 3 gigabit for HD and 12 gigabit for UHD. You need to have PTP in the cloud, which means you need multicast. Well, now there's a cloud vendor who supports multicast. Thank you very much. But it's not a standard in the industry, and it's certainly not standard across the internet. So it still becomes a bit of a challenge here. And you need really high performance networking when you start talking about these kind of signals. And you also have to pay attention to the costs of doing all this. Again, if you're shipping 12 gigabit per signal around, the cost for egress and inter-region data transfer start adding up. So you really need to focus on that and ask yourself what I need, where I want to spend this money, and where it really matters to be uncompressed. So we look at different transport formats, and my colleagues will be talking about these in just a minute. And we have 2110, which is the new SMPTE standard, not that new anymore, which is great. It's now becoming mature, and it supports uncompressed. So obviously it's got really negligible latency, and it's lossless, mathematically lossless, and because you're not doing compression, it's probably going to be the least load on a CPU, because you are paying for the amount of CPU requirement you have in the cloud as well to handle these things. It's not just bandwidth, but it's also the cost of that CPU to do the processing. And if you have to do a lot of CPU to do processing, you may be constrained on how many signals you can even run in an instance, which may limit what you can actually do. There's NDI and NDI-HX, which are both proprietary systems from Newtek. There's JPEG XS, which is now a standard, which is visually lossless and gives us 10:1 compression. So that's going to be attractive. And the real question there will then come, okay, so we're getting 10:1 compression, so we're saving on bandwidth, and we're saving on networking, and we're saving on transport costs. But what is it going to require in the actual virtual instances to run this? And I'm looking forward to hearing the answers to this in the CPUs, because it was really originally developed with, I think, around FPGAs and GPUs. And by the way, if you don't know this, if you run a compute instance in the cloud that has GPU, it's going to be a lot more expensive than a CPU-only instance. So that, once again, we're watching that. And lastly, there is CDI, which is what AWS has done to make ST2110 actually function in the cloud. It's not pure ST2110, as Evan will tell you shortly, but it is a way of, they managed, because 2110 itself won't work in a cloud, to do something to allow uncompressed to work in Amazon. So we'll hear about that. So these will be very interesting, and you're going to have to pick which one of these you use and where you use it to make cloud production workflows work. So all these formats look and maintain the current workflows, optimizing latency versus bandwidth versus cost. But I'm going to ask you all a question now. Are we still hung up on the old ways of doing things? And is this constraining us from really getting the benefit of the cloud? Is it time for a new mindset and a radical change to our process? Can we rethink the entire production workflow? Can we be willing to trade off past practices and requirements to enable new opportunities and possibilities? Can we rethink latency in live production? And is uncompressed really required? So I want to throw those questions out there, and I want to show you a couple ideas and answers just to show you that you can say, Peter, you're nuts, you're crazy. Maybe not. We'll see. So what if we really embraced the cloud and created new models for live production? We actually embraced latency and used it to our advantage rather than fighting it. And we leverage these unique cloud capabilities, massive on-demand computational resources, dynamic orchestration, and true consumption-based costs. Because if you build a production facility today, you're paying for it 24/7, 365, whether you're running any workflow through it or not. But in the cloud, you're only going to pay for this the moment you're actually using it. So I want to talk about another project that was done by a fellow SMPTE colleague, a guy named Richard Welsh, who started a company called Sundog back in around 2012, I want to say. And this is a perfect example of how you move to the cloud and how you rethink what you're doing and how you make the cloud really work. So this is in the film industry, the digital cinema side, and where they do very computationally expensive processing. So if you want to convert a 2D movie to a 3D movie, you can go to Skywalker Ranch, and your colorist and your cinematographer and your director can go there, and they can set up this process, and then they can run it through their supercomputers there and get in the queue and wait a week and then come back and see what the process looked like. And you're paying for people to sit there and wait, and they're having to see something, you don't like it, they come back and do it again. And these things are very computationally expensive. So if you look at, for example, doing a 2D to 3D process, it is something like 56.1 trillion data points per frame of video that are processed. Phenomenal amount of processing, right? Well, what Sundog did, Richard is brilliant, he threw this up into the cloud and he spins up 5,000 cores of compute simultaneously. So he's building basically a massive supercomputer on the fly to do these workflows in real time. 4,000 of these workers are probably handling, each one doing a line of video in 4K. And the other 1,000 are actually managing the workload across those 4,000. And then he got really clever. And Evan, you don't want to hear this part because this is secret news. But what if you go to the cloud, so, you can pay full price for a compute instance, but you can also buy it on the auction or spot market and buy it like on 10 cents on the dollar, a compute that's not being used, excess capacity. So you build an algorithm that runs all around the globe, finding excess capacity. So he's only paying 10 cents on the dollar for all the computes that are running this. So now instead of this being $5,000 an hour to run this, it's $500 an hour, which is less than you'd pay for the people sitting there waiting for the other thing to happen. So it became very economical and was quickly adopted by the industry, by a lot of people to do their post in the sky. So this is an example of how you don't just move your workflow to the cloud, but you really get the benefit of the cloud. You leverage what it's capable of. You really leverage the massive compute capability, and it transforms your normal workflow. So what used to be something where you'd take a month to go through post can now be done in a day with this. And that's truly changing the motion picture industry. So is latency really the enemy? Or maybe how I learned to stop worrying and love latency, right? Taking after Dr. Strangelove here. So where latency matters: transport, latency of the camera and source feeds to the cloud; production, latency of processing engine, the switch point to operations, because if I push that take button and it doesn't switch for another second, it's really hard to do a live production. And of course, distribution, which is latency on the output side, which we're not going to really focus on right now. So if I look at live production, I'm going to have my game in the stadium, and I'm going to call that event time. And then I have latency going from that game to my processing engine in the cloud. I'm going to call that my engine time. So there's going to be a latency between those two, which is the transport latency. And it's made up of everything from encoding to distance and latency to protocols to protect it and such. And then My engine's running in the cloud, and I'm going to connect that to wherever my physical work surfaces are, and my operator is looking at monitor walls. And that's going to be a control and monitoring latency. And so we have two different latencies we're focusing on, the transport latency and the control and monitoring latency. Now, in this model, I have camera operators at the stadium running cameras, and I have a TD and a director sitting back in the control room telling them what to do. But that signal that the TD sees travels through both of these latencies before it gets to that operator. And so if the operator sees a scene change and tells the cameraman to do something, and the camera moves 3 seconds later, that makes it really hard to direct the show. So this becomes a problem. Dealing with these latencies is going to be a really big issue in how we do with this, which is why we're talking about uncompressed, or we're talking about JPEG 2000, or I'm sorry, a JPEG XX, because we're actually able to keep the same kind of latencies that we normally have in on-premise production facilities, because we can actually also co-locate, use a cloud system that's in our region, close to where we're actually doing work, so the latency between the cloud and us is nominal. You don't want to go across country. You want to pick an availability zone next to you. But there's still latency there, and it's still a challenge. And that latency is, and the question is there another way we could do this? So we've been dealing with latency for years in news gathering. We've gotten used to it and learning how to deal with it. And the source latency really only matters for multi-camera shoots, where the camera operator is being directed at the event time by the director and is not at switch time. But how do we overcome this latency? What if we treat latency as something we could add to improve production? What if those cameras could be directed differently? What if we can move the camera operator into the cloud? I know that sounds crazy, but what if we could move that camera operator in the cloud with zero latency relative to the processing? So if the camera operator was here and we moved them into the cloud, then the only latency we'd have is this one pipe right here for the monitoring and the control path, which is trivial, but the monitoring. So we only have to worry about one latency link there. Well, look at this. What if we ring the stadium with cameras? And they're all fixed. There's no operator in the stadium. And we take those feeds, we bring them into the cloud, we use volumetric camera processing, and now the operators are sitting here and they're able to synthesize whatever camera position they want and robotically, not control the cameras, but what the camera thinks, what you're creating virtually from those cameras. And you're synthesizing any camera position you want. And what's really cool is not only can you basically do that real time against that system in the cloud, but you could also be creating camera positions you could never get with a human. And imagine what that would look like. So I want to show you a couple examples, because this is not as far-fetched as it may seem. But effectively you see a scene change and you can virtually control that camera and go right with that scene. So a way to do this, well, you could shoot in wide, like in 4K and 8K, and do pan and scan in production, or you could use multi-camera volumetric arrays and synthesize the shots in production. In both of these models, the camera shot is directed at the switcher time, not the event time. In-person camera operators might not like this, of course, because, I come out of that world where we used to travel every day and do remotes, and it's like a bad day on the road beats a good day in the office was our motto. But camera operators are now remote and still need to drive the shots. So we'll still need them, but they're probably working from home or working from a facility. In production, can see the event slightly ahead of time because we can look at it ahead of the delays, or even add delays before it gets into the volumetric switching and anticipate shots. So now we can actually see something happen and make the switch happen before it actually really happens in the system. So now we have these effectively creating virtual jib cams, sky cams, and POV cams, and we can even add AI to really enhance that experience and help with the control. So take a look at this. This is an example from Canon where they're doing this, where they're taking these fixed array of cameras around the stadium and creating what is effectively a virtual jib cam move. It's pretty cool because now covering a sporting event is starting to get a lot closer to what esports looks like, where it was totally synthesized from the beginning. And here's another example. This is Intel's version. This is their TrueView immersive technology. So again, this is the same sort of thing where I'm taking all these cameras and I'm able to synthesize any position I want and create these rotations and create these moves that I could never do in real life. And it creates a whole new viewing experience. In real life, you would never do that because you'd be doing jump cuts. across that line of access, and it would be very hard for somebody watching the game to figure out, oh, the team that was running left to right is now running right to left. But when you actually take the camera, move it like this, you perfectly understand exactly what's happening. And now you're totally absorbed into the game. So think about that. We're able to do this, and we're going to leverage all that compute power in the cloud. Instead of worrying about latency, we're going to say, well, take that latency, we'll make it and actually enhance our ability to do production, and we'll use that compute power to do production we never could have done before. So I wanted to just throw that out there as we hear the rest of these, that maybe one of the answers also is not to do this the way we used to do it and not just try to replicate those workflows in the cloud. So thank you.
Thank you, Peter. Lee, if you want to spark up and introduce the next presenter, I will hand over control.
Okay, and just a reminder to everyone, we are doing sort of a panel at the end, so feel free to type in questions in the question dialogue, or you can sort of save until the panel at the end. So I have the pleasure of introducing Jean-Baptiste. He's presented at SMPTE Toronto before, however, this time he's presenting remotely from Belgium. So it's like 1:30 a.m. his time. So definitely a great appreciation for him to call in and do this presentation for us. Jean-Baptiste joined Intupix in 2007, a company creating innovative image processing and video compression solutions for cinema broadcast Pro AV applications. He leads Intupix product and business development. With the recent JPEG standardization, he participates in the design of new AV workflow and devices. Jean-Baptiste is active in different standardization committees and industrial alliances. He holds a business engineering master's degree from the Leuven School of Management in Belgium. And due to the lack of natural ice in Belgium, he also likes to play hockey, but on grass. With that, I'll hand it over to Jean-Baptiste.
Thank you, Lee. Can you hear me correctly? Just to make sure everything is running.
Sound is good. Video good.
Thank you. So I'm glad to introduce you to JPEG XS, and in particular for live production in LAN over the WAN and in the cloud. First, we see three key trends in live production. The first one is probably the one that we've been very busy this last couple of years. So this is the move from SDI to IP, essentially within OB-WAN and facilities with the standardization of SMPTE 2110. The second trend is the trends to move data and not people. This is particularly true these days with the COVID. So we see more and more remote production. We want to have more connected facilities to reach economic benefits, resource sharing, both technical and human, and reducing travel. We also see big trends in using COTS and cloud in a real-time production chain, with first higher speed interface becoming more affordable in LAN. It was an easy move to 2110 with uncompressed, but also with cloud providers working their offering, providing transport integrity between their own processes. But the uncompressed data rate are really massive. If you think about HD uncompressed, it's 2.4 gigabits per second, 4K 69.6 gigabit per second, and if I just mention 8K 60 or 8K 120, you see that this is really massive. So within a LAN, uncompressed can be realistic, but within a wide area network transmission, it's not really the best option in terms of cost. So what if we could replace uncompressed, easily managing more pixel over the existing available bandwidth that we have, while safeguarding the low latency and pixel perfect quality. That's really the focus of JPEG XS. How to manage more pixel, save cost and power, preserve quality in low latency, and simplify connectivity. These new standards, in fact, XS, just to start with the XS, means extra small and extra speed. The initiative started in 2016 with a call for proposal. Selected, and if you are familiar with the TICO SMPTE RDD35, an evolution of it was proposed and was selected as a design, and we have done a collaborative work ISO JPEG committee. And that's all. Today you see really JPEG XS solution available from technology provider and from manufacturers, and first deployment as well. So we could say that it's the most advanced standardized lightweight codec today. Yeah, so the next question is, where can JPEG XS be implemented? In fact, JPEG XS can be implemented everywhere uncompressed is currently used. So it targets not only infrastructure, but it also targets devices. It targets IP production, remote production, but also cloud processing and storage. Automotive, such as ADAS system, where you have more and more video, connectivity between chip, if you have a limited bandwidth, just to connect two components between, or within a display or within a mobile phone, if you need to reduce memory transfer, interconnectivity as well. In VR, AR headset for wireless transmission, 5G wireless as well. We did some experiment a year ago with JPEG XS and 5G, and also AV over IP, which is a big trend in the pro AV, like typically KVM or video distribution within enterprises. So it really addresses application where uncompressed is not realistic and latency and complexity are critical. So if you have more pixel to manage, if you want to reduce internal video bandwidth and power, if you want to build an efficient hardware and software-based ecosystem, as I said, without affecting the quality. So to create a JPEG XS standard, we took a different approach. While other compression traditionally focus on, as a first value, on the bandwidth efficiency, how much can I compress, we took the approach to create a codec where latency, quality, and multi-platform efficiency and complexity would be the most important factors. So that's if you look at the graph, you see clearly all different JPEG XS is from traditional distribution codec like H.264, HEVC, or different it is from intra-frame codec as well. So regarding the quality, if you try to replace uncompressed, we had to define really demanding testing process. So we have been using a new methodology that is an ISO standard for near lossless quality assessment. We selected a set of natural content and synthetic content as well. And it's what we did, it was the subjective assessment, so a flicker test where one side of the screen was the uncompressed content, and the other side of the screen we were interleaving the uncompressed content with the compressed content, and we were doing that after 7 encode decoding on the uncompressed content. So that in that test, we were not only just looking at how robust how the quality was maintained, but also how it was maintained after multiple encoding decoding passes. And the flicker test is somehow the most demanding testing you can do, because you interleave the uncompressed content with the compressed, and your eyes will be very sensitive on these temporal change in the video. So what we did is we analyzed that down to 3 bits per pixel on all the set, which is approximately a 10:1 compression, and without seeing any loss of quality. But pushing forward this kind of testing, or if you don't do the flicker but you do side-by-side or other, or if you use less demanding content like natural content, film, TV content, we have observed that we were able to compress much more than just what was made by that experiment. Also, we look at the degradation, which is something also important. What kind of artifact the JPEG XS codec could produce if we would use it out of its operating range. If you want to compress more, let's say if it's not the main feed but just a monitoring feed, you could decide to compress it in a more aggressive way. So in JPEG XS, you will get a smooth degradation, no blocking artifact, because it's also a codec that is based on a wavelet transform, like a previous JPEG 2000 codec, for example. So multi-generation means that you compress, decompress multiple times, and just the PSNR will remain the same across these multiple encoding, decoding. So we also look, and that was a constraint from the call for proposal of JPEG XS, not only to meet the expected quality, but also to meet the expected minimal complexity, targeting multiple platforms, so both hardware and software platform. So JPEG XS is really the smallest codec for FPGA at that efficiency today. So what our experiment at Intupix is, we have been able to fit several FPGA design for customer with a lot of encoders, decoders fitting in the same chip. We have within JPEG XS multiple profile for lower power, lower logic. We have a very low internal buffering, because the compression only use a few lines of buffering to compress the frame, while other intra-frame codec typically will need to store 1 or 2 frame to write and read in a memory. If it's interframe, you have the GUP, so which impact both latency and complexity also. So the story is very different with JPEG XS. In the key requirement, we had to meet expectation to fit, for example, on specific Xilinx device or Intel device, 4K 60 frame per second encoders, decoder, and these devices are somehow a bit low cost. So JPEG XS high speed in software. In the design of the algorithm, we took care to have an optimal syntax, offering various degree of parallelism to be optimal when it has to target a GPU architecture or CPU architecture. So it can exceed regular editing codec performance. And from observation we did, it's 5 times to 9 times faster than the JPEG 2000 ISO standard. So JPEG XS really offer best trade-off between cost, power consumption, and quality. And because I think that was also requested by the previous presentation, I wanted also to share the latest advanced that were done in CPU implementation during the COVID. So from the numbers that were shared to the industry previously, we now reach a really significant speed in CPU in just using a 6-core Intel Xeon here. You can see that we are really close to 8K 60 frames per second, or we could support up to 10 stream of HD 60 or 3 stream of 4K 60 using a 6-core. And the encoder is very symmetrical. So this is really promising, and I would not say that these numbers need to be taken as they are. As they are today, but the JPEG XS standard is quite new, and future implementation and future improvement can still be done. So, but you see that it's on a 6-core CPU. The performance are quite amazing. Minimal latency. Also at that level, I would say that on the FPGA, we've been sharing that for JPEG XS a lot. So for hardware device that we can reach less than a tenth of 1 millisecond, so 0.1 millisecond. So typically it's like 10 lines to encode, 10 lines to decode, but you can, depending on the profile that you are using. On a CPU, also you can reach just few lines of latency, so you can go far below 1 millisecond for a full encode plus decode in CPU. So we know that a human can detect a latency only above 13 milliseconds, and I would say you could cascade a lot of JPEG XS encoding, decoding without perceiving any latency. But of course, you have to take into account a lot of parameters in the live production. It's not just the latency of the codec, it's also the latency of the interface network that need to be taken into account. So JPEG XS is designed also to be future-proof, so there is somehow no limitation in the resolution. Chroma format, it supports 444, 422, 420, monochrome, and we are even working for future profiles supporting raw Bayer compression. In terms of bit depths, it can go from 8 to 16 bit. HDR is supported. There is no limitation in frame rate. And an interesting feature is also it's the internal scalability of the codec. So somehow the proxy is part of the XS master. So JPEG XS has a multi-resolution flexibility. It can offer up to 2 additional level of resolution. So to give you an example, if you have a 4K video stream, or as illustrated here, 8K video stream, you could decide to just decode the 4K resolution of it or the HD resolution of it. When you do that, you will easily build a monitoring system consuming less CPU resource or GPU resource, but you can also ease some transcoding application to move from a proxy to an H.264 resolution for format, for example, to go over a limited network or something like that. So JPEG XS also is an ISO standard, so it delivers open specification, ensuring interoperability. But an important work has been done also with other standardization committees and industrial organization. Today, JPEG XS is published as a standard. We work on future profiles like the raw Bayer compression, some extension from matte lossless 420, or things that are somehow not highly demanded for IP production, but that would be useful for other areas. The RTP specification of JPEG XS has been done and is in final review. it relies on the SMPTE 2110-22, which is the encapsulation of compressed video for SMPTE 2110. We also specify MPEG transport stream encapsulation, MXF format, MP4 format, and even HEIF format, the same container used by HEVC, if you're familiar with that one. So what we mean with bandwidth efficiency in HD, 4K, and 8K? If we take the typical bandwidth at the best quality, we would typically target 3 bit per pixel. So this is the upper limit that you see here for this resolution. But depending on the context, the content, you may want to compress a bit more. We did some experiment at Intupix, typically for 4K at about 750 megabits per second, 8K. Depending on the size of your 8K screen and the content, we did a demonstration at NAB a year ago of 8K at 2 gigabits per second. Of course, the screen was so small that it was not really easy to distinguish some noisy artifact, but it just showed how powerful can be the compression standard. So what is interesting also is that if you consider existing infrastructure, of course, we know that high bandwidth infrastructure in LAN are possible, but Cat5e cables are very accessible. In my laptop, I can connect a gigabit feed. So it's important to look at JPEG XS also as an enabler to use simple Cat5e or Cat6 cables. So moving forward, live IP production with JPEG XS can enable to connect a remote production, can enable to move your workflow to cloud production, can also enable to be used in a LAN within some facilities that want to optimize the number of stream, upgrade to feature resolution, be in, access through a gigabit network. This really offer a huge, huge benefits for live production at that level. So in the LAN, you can target cost-effective infrastructure, cheaper cables. You can reduce storage cost, as you can also record your file in XS. You have a friendly bandwidth for PC software. You don't need to redeploy wires if you have a Cat5e or Cat6 cables. Over the WAN, it offers cost effectiveness with 10 times a smaller bandwidth. It will offer reduced IP packets. It will ease the remote production, the contribution. And in the cloud, it offers very efficient CPU performance, but also GPU and FPGA, and all these 3 platforms are somehow available with a very low latency. So it's really enabled to overcome the uncompressed limit, preserving all the benefits of a compressed, also such as quality, latency, and you get somehow more value by using JPEG XS. So my takeaways is like JPEG XS offer a true alternative to uncompressed to connect to the cloud, the WAN, and run in the LAN. It preserves the quality. It offers software firmware upgrade capability to new formats in existing infrastructure, and it guarantees interoperability thanks to the use of open standard and specifications. Thank you.
Thank you, John Baptiste. Very great. Lee, if you want to introduce John, I will move things over to him.
Okay. Well, I have the pleasure of working with John every day and getting to introduce him. We're going to continue on that theme of the beard of knowledge for this section of the presentation. John Mead has been working in the field of digital high definition television since its North American inception in 1990, first as part of the AT&T Zenith team, and then as technical lead for the Grand Alliance encoder, later as engineering manager and general manager of Lucent's Digital Video, Astra Digital Video, Harris Broadcast, and now Imagine Communication. Today, John is the CTO of Networking and Infrastructure at Imagine Communication. He has 2 degrees from MIT, and he's a SMPTE Fellow. Over to you, John.
Mute button. Find the mute button.
Yep.
Everybody, I'm John. And I just want to give a shout out to Mike Johnson, if he's still here, who's one of our newest SMPTE Fellows.
Yeah.
So I had the luxury of going last, and since we're way over time, I'll go short and employ some of that compression stuff we talked about. There's a lot of work going on how do you move this stuff to the cloud, how's it going to work, what's it going to do, but who's doing this work and where is it happening? So this is similar to a talk I gave at ATC a couple weeks ago, but basically there's this organization called AIMS, and there's a lot of organizations. We'll talk about them all very briefly. But AIMS started 5-6 years ago now as with the mission that you see here to adopt this set of common ubiquitous standards-based blah, 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 blahs. And the words I really want to highlight here are one set and interoperability, because the whole idea was to avoid the unsavory fate that happened in the audio world, where at one time there were 12 ways to do audio over Ethernet, and say, how do we have one set of IP standards so that as an industry we can move forward quickly? And of course, the key thing there is that they should be standards, whatever it is that standards means to a given person. And, you know, SMPTE is a standards development organization, official, ISO, blah, blah, blah. There's also AMWA and BSF and other organizations that are trade associations and have different credentials. And most people don't care that much about those distinctions, and that's okay. The goal here is to get her done. So there's a lot of organizations that are involved. So SMPTE, you've heard of, AES, deeply involved in the audio world of IP, but also in the protocols around controlling some things. AES 70 and its related OCA Alliance, a very interesting set of work that's gone on there. The IETF, there is this RTP payload format for JPEG XS that is in this state of done but not finished in the IETF, and we all hope that JB and everyone else can drag it over the finish line in the next meeting there. The VSF, not to be outdone, has at least 3 different working groups working on similar related stuff to what we're talking about here today. How do you do 2110 over the WAN? How do you do ground to cloud and cloud to ground? How do you do JPEG XS over 2110? And of course, the Advanced Media Workflow Association, AMWA, has done all this work on this great NMOS thing. And how does that relate to the next challenge at hand? Some of you have heard of the Joint Task Force on Network Media, the JTNM, which published this very helpful TR1001 document. Helpful hint, there's a new version of that published the other day that has some core agendum and some little tweaks, but nothing giant and new. The goal was not to make giant changes. And in parallel with all this professional media work that we're doing, there's a whole cadre of vendors now looking at the same set of problems in the, let's call it the multimedia space. So enterprise, corporate, colleges, things like that, where it's not about producing television programming, it's about producing shared lecture spaces and shared projectors and shared multimedia elements within large campuses. So there's a whole group under the general moniker IPMX that's deeply involved in that, and taking ideally many of these same technologies and adding the little bits, so things like HDMI hot plug detect and EDID shuffling between monitors and devices work. Very big activity happening just now. So look for information about that. It's the same set of people for a different market, but same technologies. So what was the goal of AIMS? Well, AIMS has a technical working group but it's mainly a market-focused organization. And the goal as technical working group is to maintain and extend that roadmap and to take on whatever technical tasks relate to moving that roadmap forward, good direction. So our first roadmap, this was only a few years ago, right? It was 2022-6 and AES 67, and oh, that VSF Tier 03, remember that? And so that was how we started, and we decided we would only add things on the roadmap when they became real. So of course, by a year later, we had added AMWA and NMOS, and by 2 years in, we shifted everything to 2110, all about 2110, and that's good. 2110 was published at the end of 2017. Here we are at NAB 2018, talking all about 2110 and NMOS, and this is kind of the state of affairs on the ground. At +3, so NAB of 19, we added, the -40 and added some bits and pieces around that AMWA stuff, but it was really the core is all there. And there's lots of facilities around the world on the ground getting built out with this. And of course, NAB 2020, well, we didn't change the AIMS roadmap at NAB 2020. But what's that mission thing again? Well, set of common standards, interoperability, yada, yada, yada. Are we there yet, you might ask, because haven't changed the core roadmap. Well, so what would be next? Well, within a facility, we got data plane, we've got environment, we've got connections. You could argue we're done. But, there's opportunities to be better off, right? And those opportunities are mainly around common control, status and monitoring APIs. And so there is work in progress starting in AMWA and other groups around how do we attack common control and status, and how do we move that ball forward? Because we're all tired of writing drivers for things that are the same fundamental function on every device. And NMOS does a great job of connection management, but I'd also like something I can call to find out later how it's going. How about between facilities? Here we are an hour into this meeting, and that's what we've been talking about. Well, there's not a rich body of finished work on the standardization of facility to facility transport, but there's certainly all the parts are right there. We've just talked about all the parts. So JPEG XS over 2110 between facilities. So there's a working group in VSF that's all about that, and come to the meetings. It's a great group. We're working on the technical recommendation of that. Now, what about between instances within a cloud-like environment? You could use this JPEG XS to get there, to get home. What about between? Well, that's a work in progress. Again, there's a VSF working group that's looking to take the CDI APIs and, document whatever additional technical recommendation would go with how do you use those? How do you set the timestamps? How do you organize the flow of time so that, as Peter said, latency can be your friend, or at least your managed, frenemy, rather than just this murky unknown. So how's this look in practice? Well, if you're going from the ground to the cloud, and this is from the VSF cloud to ground, ground to cloud working group, that's very hard to say. There's an interoperability point there that's really in the network. You have a whole stack of from your signal down to the IP packets, and that's how it ingresses to the cloud. Within the cloud, presumably you have some catcher app, and then you have a live signal. You could do whatever you're going to do. And on the same side, same way in reverse, you have some thrower app in the cloud that does whatever it's going to do to get to the ground, and you can document that set of standards, and they're pretty clear what they are, right? 2110, 22, 30, 40, some kind of bundling of the flows so they're a single connection going through the WAN, because that tends to survive better. Within the cloud, okay, it's more interesting because you don't really want to try and make the interoperability point something that's untouchable and unmeasurable deep inside the cloud. So that's the beauty of this stuff Evan just talked about, where you create an interop point that's really in the middle of that stack, that's really a definition of here's buffers and some metadata, and I'm going to hand them off, and they're going to magically appear in the next instance. And maybe you don't believe in magic, but when it works, it's pretty useful, whether you believe in it or not. So that's really the other trick here, is to define that middle interoperability point so that you can have apps from Imagine, from other people, and you can plug them together, whatever plug means, in an orchestrated cloud-like environment and make television happen. So that's the state of play in the standards world and the groups that are doing it. So VSF is attacking these kind of definitions, and all the right players are in the room and we're talking it through. SMPTE did its job with 2110 and is involved going forward in other things. And again, there's some VSF work going on in defining this ground to cloud aspect as well, but it builds on JPEG XS and all the other work. And I'll just point out this little joke at the bottom. The signal plane's the easy part. Really, how do these parts within the cloud find each other? How do you know, how do you hook those apps together? How do you work out security barriers? What's the cloud equivalent of a PGAD? Very interesting problems, but I'm sure as an industry we'll work them out. So that's who I am. Paul, do we have any questions tonight? Paging Mr. Briscoe.
Well, we just may have some questions. I have a few, and maybe Tony, you could unmute our other presenters, and we'll turn this into a panel.
If all the presenters can spark themselves up and unmute yourself.
Yeah, I didn't think I would hear the term PGAD for a long time again. I was really pleased to hear that. I had to explain that to a lot of people what PGAD means.
It's a permission to grant additional distribution, something like that.
Right.
It's how you can pick up the end of the football game as a newscaster to get the highlights reel without really having rights to the whole game.
Or it's actually just used to share pull feeds, and you have a right to subscribe into it. And PGAD. Yeah, but
I used the term today too for some reason.
Wow.
I have no idea why.
Amazing.
I was explaining pool feeds to somebody.
That's really cool.
It goes against every aspect of security.
Yes.
This notion of you just call up Joe at CBS and say, Joe, can I get that feed? And Joe says, yeah.
I'll put you on the PGAD. Yes.
Fantastic. Well, gentlemen, thank you all for your presentations. They were to a person fantastic, and I think the crowd enjoyed everything. And we have a number of questions that have come in, so if that's okay with you, I would like to throw them at you. I think I know who they're intended for, so I'm going to try and target the question to an individual, and then I'd ask that after that answer, others chime in with an opinion, because opinions are interesting too. First question. So NDI wasn't really talked about this evening in any detail, but Jean-Baptiste, can you give us maybe a little comparison performance-wise in terms of image quality and latency between JPEG XS and NDI?
So at Interpix, we did not perform analysis of how NDI would scale in complexity in terms of latency. I would say in software or in hardware device. I think they claim a few lines of latency. In software, that might be close to less than 1 frame, and in FPGA or hardware, I have no idea. I don't know if we have to look at how many lines versus how many lines when we compare XS. I would say probably, well, benefits of NDI for the industry was that they were able to pick something that was directly available and easy to integrate. But benefits of XS is that it brings an open standard and interoperability between vendors. You know what is inside. And in terms of performance and speed, honestly, XS has moved so fast. Well, you probably saw the slide that I shared, but that I didn't look too much on how many HD stream we could do on a CPU processor. But I think that XS now is getting better than NDI from what I have as a feeling. But yeah, I should recheck that. We don't have access to purely an encoding instance or decoding instance. So it's NDI is something mixing up an IP protocol with a codec. So it's difficult to make a clear comparison.
Other presenters, any opinions on NDI and how it fits into the broadcast quality world, if we could call it that? Blank stares and silence. Okay, that's fair game.
Yeah, the only thing I can say on XS is we took really care of looking not just at natural broadcast content, but also desktop content. So, like if you want to build a KVM, I don't know, or NDI would behave on a fine text and things like that. I have no idea.
Yeah, we're not exactly comparing the same kind of fruit. Anyway, it's a little bit apples and oranges. You know, they're both tasty fruit. But NDI is very different from XS in that it's bundled with transport, it's bundled with other services and audio and all of that. But it's a question, you know, that I think a number of people have on their lips. So I realize, of course, XS was designed to different goals as well. NDI was designed to fit in a gig E and provide the best video quality possible, you know, within that. And several years ago, XS was, of course, designed a little more formally, and hence it's a different kind of standard. So thank you. A question for Evan regarding CDI. The flowlets, are they simultaneous and redundant around the network? So you spray them across the network. So is there a bandwidth overhead in SRD, and does the user pay just for the payload transported, or do they pay for all the scattered bandwidth as well?
No, it's not redundant. Each of the flowlets has a short ARQ buffer. So it's not like, so in like a Zixi or a RIST or SRT, it's a larger ARQ buffer that you tune in milliseconds. But with this one, they run in parallel, but not redundantly like that. So it's really spraying packets across many of the flowlets. And then if one of them has an issue, the retransmission happens on one of the other ones, but it's measured in microseconds, which is how you end up still being able to get the whole frame in time. Okay. And then the cost question. I guess there's two ways to interpret the question. You can interpret the question as, does it cost any money to do this? The answer is no, because when you're sending traffic within an availability zone, that's not billed. But if the question was, does it cost my network performance? Like, is it a network performance cost in terms of just bandwidth on the wire? I guess the answer is still not really, unless something really, really bad happens that I can't imagine at the moment. But usually the transport rate is about the same as you'd find on SDI with a little bit of overhead.
Okay, cool. Thank you very much.
Sorry,
another question.
It's less than SDI. Sorry, I forgot. It's less than SDI because we kept the essences separate like we did in 2110. So it's just the video essence, for example.
Yeah, not all the white space, as is appropriate. Cool.
Thanks.
Another one, selecting a technology such as CDI or JPEG XS is largely driven at the moment by what's supported in the products the customer wants to use. Assuming all desired signal formats are supported, does it come down to measuring the cost of each format in transport data cost versus CPU processing cost versus network bandwidth limitations? I'll throw that to whoever wants to speak to it first. Maybe Peter kick that first, but whoever.
Sure.
Sorry, I think you haven't jumped.
Sorry.
I was going to say it's a good question. That's exactly the conversation we're having is like, do you want to use more CPUs or do you want to use more network? And it depends what your application is, really. Like, you know, Peter works at TAG. It's a multi-viewer, right? You need like lots of signals going into one instance maybe to do something like that. Whereas if it's, you know, a playout application, you're in a different situation. So everybody has their own perspective on it. How about that?
Yeah, so I'm likely to run out of input network bandwidth coming into an instance doing a multi-viewer with UHD. before I run out of compute power potentially. So therefore using JPEG XS to get more inputs in gets the balance back in space. So that's exactly right. And then there's also the cost of each of those. So the cost of CPU to manage the JPEG XS versus the cost of a higher network bandwidth if I'm going in and out of the network. So again, I think at the end of the day, one of the most challenging parts of doing anything in the cloud is finding how to create efficiencies that make the cloud cost effective so that you can actually really grow your business.
Right. And I think the other factor we really have to caution people about is what you don't want to do if you're a television engineer trying to make content and monetize content is worry too much at too low a level of the stack. What you're really looking for is a technology solution that's actually engineered to work and interoperable across vendors. So you can pick the playout system you want, you can pick the ingest system you want, you can pick the multi-viewer you want, you can pick the other things you want, and organize them together in an interoperable workflow. If you start engineering things at too low a level and you say, well, I want for my system to do this one thing completely backward because I have a theory of how that's going to save money, I almost guarantee it's not going to save money by the time you're done, because your system will be a snowflake and every piece of equipment you buy is going to have to be custom to work backward the way you asked for it.
Yeah, good point.
That's true. There's something I thought of to add too, which is the method of CDI, this flow-lit transport thing. We happened to do full uncompressed frames first because we realized that we could, but it's also reasonable to think that in the future somebody would say, what if I want to just put a compressed payload within that reliable transport? And I think that would be a reasonable conversation to have at some point as well.
Excellent, very good. Thank you. Question I'll just throw to everybody and somebody can pick it up. How would you orchestrate an end-to-end live production workflow? What tools would customers use to automate the entire process of orchestration? So here we're talking about, throwing up a system for a pop-up event.
So, I mean, generally, our approach is to try and leverage things that the IT industry uses for orchestrating, compute workflows today. So, and those tools change about every 18 months. There's a new one that pops in and one of the old ones pops out. So the flavor of the month last year was things like, Chocolatey and Puppet and Chef. And now there's, a lot more work around Ansible and so forth, but they're all variations on, scripts that do things and that are parameterized to your application needs. But this kind of is a transition of a different sort too, that when you built a facility 10 years ago, you wrote a spec and you had a big engineering committee and you spent a lot of effort and you wrote a spec and you kind of designed it in block diagram, and then you built it and then you operated it for however long, making almost as few changes as you could possibly get away with.
Yep.
Now we're talking about a very different methodology where you say, look, I'm going to have some maybe modeling language or moral equivalent of a modeling language that's going to describe my workflow, and I want that to get instantiated on the fly and work great. And that's such a different workflow that it's going to take a while for the tool chains that do that to catch up. And equally, it puts the engineering part of the television operator in much more of a, not just monitoring did it turn on, but being responsible for that workflow articulation. So it's going to take a more engineering effort in the sort of day-to-day operational workflow management to do these things that spin up and spin down and morph and change. I look forward to the view, the worldview that Peter espoused at the beginning. But boy, do we have a lot of getting there to do.
Well, I already did all that. What do you mean it's done, right? It exists now. But John actually really hit on with something else really interesting, because there's a cultural thing here. Because if you come out of the broadcast industry, the culture is if it fails, you're fired. And if you're in the cloud industry, it's like fail fast, move on. So how do you people who are afraid of failing to be test drivers in the cloud and try new things constantly. And so we had that cultural shift. We're actually battling at the same time all these other things we're working to get done.
You know, and an interesting other problem comes up from all this because, you know, I think all of us having built and developed facilities in the past, which are, you know, big rigid things you build, you operate, they work the same day to day. And, you know, upgrading it to a new capability is actually a major thing. And fast forward to now when, you know, you expect when you run the app the next time, oh, it looks a little different, has additional features. So that's just how life works. And so these are dynamic environments that, you know, require a totally different mindset from the operations people who have to live with continuously evolving, expanding, you know, rolling production infrastructure. So not just orchestration of them, but just the dynamic nature of workflows going forward is really going to be a social change. It's very interesting stuff. Thank you for addressing that one. I have a little bit of a tangent kind of question. And it's a touchy subject because this is a SMPTE presentation, but got to ask, what's the future place for standards such as SMPTE as compared to specifications such as SMPTE, VSF, EBU, and AMWA, as compared to just open software and proprietary SDKs? What is the future for these things in the industries? I mean, in the past, it's been standards, standards, standards. Anything else was special. We moved to the internet era, and while there are standards, ironically, internet standards are requests for comment documents, but they are standards. Has the world changed? Are we moving away from standards to simply common practices, open source software? What are your opinions on that? I'd like to hear each of you speak to that.
Mm-hmm.
John?
Yeah, so what I would say is, I mean, we like standard, but we don't want to stop innovating. And somehow, at Interpix, at least in the compression field, that's how we see that JPEG 2000 was an existing standard that our company took, and we were the first company creating an ultra low latency JPEG 2000 codec that was beyond the standard and adding new innovation to it. And a few years after, we did a VSF specification for that ultra low latency. And I think we'll need to be in that dynamic where you have new things coming a bit before standardization, and you need to create some interoperability point. And sometimes it's through a standard, sometimes it's through a recommendation, or sometimes it's because there is a major vendor doing something and you have to follow.
Yeah, I think this question to me is very much about what level of the stack you're at. You know, if you think about building materials, right? I mean, nuts and bolts and washers, they're extremely standardized. But where are the windows in your house? You know, are they here? Are they there? That's not so standardized, right? And the same thing is going to be true in our industry. So things like how are the Ethernet packets formed, or the JPEG XS to the extent that it's like wire level coding on video interfaces. Those things want to be really standardized because they're going to be baked into silicon, they're going to be baked into implementations, and they're complicated, and they have to be right. So that's like the, you know, the IEEE level, you know, what is 400 gigabit Ethernet? There really can only be one spec for that. Well, apparently there's two, but there can only be one. And then you start working your way up the standard. You get into things like these, you know, device control layers like NMOS. It's really helpful that there's a specification, but it needs to have the right flexibility to adapt to the situation and to be able to be modified without a 3-year, 1-year review to change 5 lines. That would never happen in some organizations, right? And then you get further up the stack to things like we're talking about these workflow languages for instantiating and tearing down services. Those are sometimes just specific per customer. You know, they're just bash scripts or piles of bash scripts built by somebody. Others, sometimes almost no standardization, or they're as standardized as the last commit you did. And so that's really, I think it relates to what layer of the stack of application you're at in terms of what needs to be super standardized versus what needs to be an agreed spec versus a, you know, maybe a less agreed or less common spec.
Evan, any comment on that?
I should have gone before John because he said it so well. I really have nothing to add. That was,
Well, that's a
I really agree. I think the other thing, the only thing I'd add is that as everything becomes more available in software, it enables people to go faster than they could before, and people will innovate faster than the standards bodies can keep up. And so there's nothing we can do about it, really. That's just going to happen. So people are going to go and do stuff because they can, and they couldn't, maybe they couldn't before. So I'm looking forward to seeing where that brings us.
And it's interesting
Good
because
answer.
the internet itself isn't even built on standards. It's built on best practices and recommended practices. ARQ, for example, everything we're talking about with RIST and SRT is not a standard. It's a document. You know, so you know, we already are building an entire house of cards based on something that doesn't have standards at the bottom. You know,
Right.
it's working just fine. It's fine for as long as the internet's been around.
Right.
Yeah.
And it's funny too, because the IETF was at the outset a very fast and loose organization. And then over the years, it's become as process bound as anything. I mean, look at what we've gone through trying to get this simple JPEG XS RTP format through the wickets at the IETF. It makes SMPTE look fast.
Right. God.
But it's also what they show with CDI at Amazon. They can publish it on GitHub. They can make the SDK available, and it gets adopted. And you know, and now it's, you know, and it's going to become if not a de facto standard, you know, something that others might use even outside of AWS potentially. I don't know, but you know, you sort of have set the new benchmark for how you make technology available.
Yeah, it's interesting a little too, because standards, of course, as John points out, nuts and bolts are highly standardized, as they should be, and stuff baked into silicon needs to be highly standardized. As we go forward, less and less standardized stuff needs to get baked into silicon, so we can perhaps tolerate a lot more give and take and evolution, you know, in what used to be called a standard and today is an evolving, you know, technology. So it's very, very interesting, and it's something, of course, SMPTE is paying attention to. SMPTE recently has introduced the concept of a specification, which is less than a standard, but more than just somebody's document. And that's one good way to handle it. You can point to something on GitHub and say, here, this version of this is that, or something like that. So
and
very
I think
interesting.
they changed the name of it from specification to something else, so even that was fairly fluid.
Exactly right. But that's the whole idea. You know, we have to adapt, or we don't survive as a standards body. At the same time, we're an ISO standards body, and being able to produce those is extremely valuable for the right application.
Mm-hmm.
A few more questions, keeping an eye on time here, recognizing it's coming up to the top of the clock. A quick question here, I'll just throw to, it's probably an Evan question. How will timing work in a cloud environment? Is a PTP-like flow needed to time everything that arrives in a cloud instance, or will each cloud instance lock to the same time source, removing the need for a timing stream flow?
Both, I think, is the, I don't know if it's not really an either or. I thought it was an interesting choice of the word receive in the question, because if you're a receiver of streams, your job is to realign them based on the timestamps that are in those streams. So you don't really need PTP for that. In fact, that's how CDI works right now. If you send a 2110-22 JPEG XS stream, for example, and you want to convert it to CDI, there's you essentially preserve the origination timestamp, so that if you have a application that needs to have synchronized cameras or something like that, whether that be multi-viewer or a switcher or something, that piece of software is still acting on the origination timestamp, even if itself is not locked to that timestamp. Now, if you're the origination point of the content, that's a different story, because if I'm gonna originate a camera and you're gonna originate a camera and they're supposed to be in the same room, then those things better line up right. And so those two things need to be synchronized still. Luckily, cameras are on-prem, so the thinking is actually, and this is coming from the cloud guy, the thinking is actually your PTP clock stays on-prem and synchronizes your cameras because you need cameras, and then you send that to the cloud, and then the production switchers or whatever processing you have there can act on the origination timestamp. That gets you probably 95% of the way there, and then there's 5% left where that's not a good enough answer, and we need to have more accurate time in the cloud. Right now, by the way, the skew between the GPS and the instances, at least in AWS, is 1 millisecond. So even if you're doing multi-instance origination stuff, that's within a frame time, and you're mostly good. But we're trying to improve that. Some people say we need it down in the 100 microsecond range. Some people say get it down to single-digit microseconds. So the direction is towards more accuracy. How about that? But I don't know how accurate we actually have to get.
Yeah, well, that's a whole other conversation, and we're on a slippery slope into a very deep rat hole here. But probably the older the contributor, the more precision they want, simply because, you know, coming from the nanosecond days, it's real hard to let go and assume that video frames are good enough. But I personally think you can build production systems with millisecond timing accuracy in the cloud without much trouble. So very, very good answer. Thank you. I have one more question, and I'm sorry, I'm gonna have to truncate a couple of questions that came in just because we're gonna run out of time here and I wanna be respectful of people's evenings. And this is actually directed at Peter. Peter, could you speak to the potential market for user-directed events and how the model you described could enable that? Specifically, he's talking about viewing angle and, you know, audio to customize their experience along the lines of you showing, you know, the synthetic camera views.
So when you create a volumetric camera array, you're creating a map field of all those images from which you can derive any vantage point you want, right? So theoretically, instead of a cameraman sitting in the control room and creating the view that he wants to see or she wants to see of tracking the ball down the field or the alignment or, you know, whatever, you know, someone at home could potentially do the same thing. Of course, there's a lot of compute power running behind that. I don't know exactly how much. So there might be an economic consideration giving everybody their own control, letting them pick what they want to look at and how they want to do it. But certainly it's not different than a lot of video games are done today in esports and stuff. We saw that last week in the SMPTE conference on esports. You know, we could see this sort of thing happening. So that could certainly come down the path where somebody's going to sit at home and through a video game type console application be watching a live sporting event and actually controlling their own camera angle. And I could see, you know, we're saying, or at least creating different perspectives of the same game. One as an audience, one as a player, or one on this side of the team and one on the opposing team, you know, and so you have different perspectives. So I think that's the neat thing about this, is it's not just migrating the current workflow to the cloud, it's creating a whole new opportunity of how we enjoy a game, are immersed into it and engaged by it and actually participate in it.
So just to come back to the difficult
my friend of mine says it's like gets the audience out of the stands and onto the playing field, you know.
Okay, can you speak to the potential market? I mean, will this be all television viewing in the future where you're, you know, swiping on your phone to move the camera around?
I couldn't prognosticate how it's going to look in the future. I mean, because if you go back and look at our inability to predict the future, you know, and I have another presentation on that shows, like, you know, the things we did that a year later weren't good. Remember 3D TV? Remember that one?
I was just about to say, so is this the next 3D TV or is this the next HD TV, right? So,
you know, I mean, because I remember, like, I helped John Honeycutt and others, some big team, but building a discovery facility back in 2006. And who knew in the next year, AWS would launch, Facebook would go public, Twitter would launch, Netflix would stream its first stream, all in the next year. I mean, you look at just the rate of change even we had a decade and a half ago in the space of 1 year, you know, and you're like, how could we build a facility that predicted that? You know, so that's why we go to the cloud. And that's why I don't know how much this kind of immersive volumetric video is going to take off. It certainly creates some opportunities, but not knowing how it's going to work in the future is why you really want to go to the cloud, because you also don't want to invest CapEx into something that might end up like 3D TV did.
Well, and that's a great segue to wrap up here, because, you know, the cloud and the opportunities that we're just seeing the tip of the iceberg on the cloud here, and the opportunities it can bring to us for evolution are stunning. You know, what we talked about tonight are just bits of the technical infrastructure. What can be done in this environment, we can't even imagine yet. So it's very exciting stuff, and we'll no doubt be having many more presentations on this, on the cloud and what goes on and how it's evolving. And no doubt we'll be inviting each and every one of you back for some more insight. I want to thank you all, John and Jean and Peter and Evan. You guys have just put together a wonderful evening for us here. We really, really appreciate your contribution, and thank you so much for that. Also like to thank, of course, my co-organizers, Lee Whitcomb and Gleb Batuzov. Lee's past chair of SMPTE Toronto, Gleb's the manager on the board. Without these guys' help, of course, this would have been very difficult. And of course, Tony Miraker. Tony, thank you for riding herd and being our TD and everything else. And Tony, I'll throw back to you to tie the ribbons on it. Thank you, everybody, for letting us do this. We're really happy to be able to share the expertise of our friends and colleagues with you. And if you have suggestions for something, please contact the SMPTE Toronto section and tell us your ideas. Hey, come and do one. We'd love to hear you share something interesting that you do. So from me, good evening. Tony, over to you.
Oh, thank you. And I too want to thank everybody for being part of this meeting. It was a great meeting, and we thank you. Let me just, I just have a few, I can get my keyboard to move on. Just again, to keep the December and January meetings in your calendars, because again, there will be some interesting meetings as well. Just a few up-to-date information. If you want to get that, you can go to the SMPTE website, the SMPTE Toronto website. And if you want to get information sent to you from the Toronto section, you can become a friend of SMPTE Toronto, and that's the URL to do such a thing. Again, Facebook, Twitter, and if you want to email us, those are our social contacts. And I think that's it for this evening. Yes, again, stay well, stay safe, and we thank everybody, and we'll see you in December. Thanks very much. Talk to everybody later. Bye-bye.